Okay, hi everyone. My name is Yichen Wang.
And I'm Robert Chen.
So today we are going to present our paper, Rubik, Knowledge Guidance, Tensor Factorization and Completion for the Health Data Analytics. So when we talk about health data analytics, a very key concept is called the phenotyping. So what is phenotyping? Phenotyping is a process to... okay. So phenotyping is a process to process this raw electronic health data to the...
You can plug in anywhere. You can plug in anywhere, then you can control it. You can plug in anywhere. Yeah, it should work. Yeah, forward and backward.
Okay, thanks. So phenotyping is a process to process the raw electronic health record data to the meaningful medical concepts, which is called them phenotypes. However, there are several limitations of the existing phenotype method. First is that they are unable to leverage this existing medical knowledge, and there is high overlapping between the discovered phenotypes, and actually they are also not robust and too noisy and missing data. And finally, they are not scalable. So an ideal phenotyping method should have these 4 attributes. First is guidance. It should be able to incorporate the guidance of the medical expert knowledge. And the second one is called the non-overlap. It should be able to discover the distinct and meaningful phenotypes. And the third one is robust. It should be able to handle the noisy and missing data. At last, it should be scalable. Okay. So what does Rubik do is that Rubik actually can achieve these 4 attributes at the same time. And this slide is an algorithm comparison between Rubik and other methods. And we can actually see that Rubik has all these 4 attributes, namely guidance, non-overlapping, and robustness, and scalability. So here is an overview of Rubik. So what is Rubik? Rubik takes an observed tensor, and it does tensor factorization by factorizing it in terms of the interaction tensor and the bias tensor. This interaction tensor contains all these phenotypes from phenotype 1 to phenotype R. And also, we can see that some of the phenotypes, we have the prior medical knowledge. So we will make sure that it aligns with the prior medical knowledge. And among all these phenotypes, we should make sure that they are all distinct. And so that is a second property. And also, we also do the tensor completion at the same time. So we will complete this observed tensor to a full tensor. And finally, it is also very scalable. So now let's give you an example of phenotype. So what is actually a phenotype? So basically, this phenotype contains 3 factors, which is a patient factor, diagnosis factor, and a medication factor. And you can see from the first table that this is diagnosis and medications for this particular phenotype. And on this second table, it is a phenotype with the guidance information on the heart failure. So basically, if we know that this phenotype is related to the prior medical knowledge of heart failure, then what we can do is that Rubik will discover the relevant diagnosis and medications. So now let's go to the math of the Rubik. So this is a problem overview. This psi is our objective function. We can see that we have 3 terms. The first one is the factorization error. The second one is the guidance. The third one is the non-overlap constraints. And as we can see from the factorization error, it takes this tensor and decomposes it into the interaction tensor and the bias tensor. And the second one is the guidance constraints. And the third one is the non-overlapping constraints. And we will talk more details about these 2 later. And also there's also a hard constraint, which is the completion constraints. And also we also have the sparsity and the non-negativity constraints. This sparsity constraint is very important for this interaction tensor because we would like these phenotypes to be much more sparse and much more meaningful. And also there's a non-negativity constraint for this bias tensor. So basically this bias tensor captures the overall characteristics of the data set. And now this is first the information about the guidance constraints. So basically, we can see that we want to learn this factor matrix, which is contains a collection of phenotypes on the diagnosis mode. And sometimes we have the prior medical knowledge of the diagnosis. For example, you can see from the first phenotype that we have the diagnosis of the hypertension. We know that this phenotype is kind of related to this hypertension. So basically, we have this hypertension and secondary hypertension. And for the second phenotype, we know that it is related to the diabetes. Then it will be there will be non-zero elements on the diabetes code, diabetes 1 and diabetes 2. So basically, we have this prior knowledge of the guidance matrix A hat. Then what we would like to do is that we would like to have this factor matrix A and this guidance matrix A hat to be as close to each other as possible. However, we only have limited number of guidance knowledge. So what we do is that we will use the matrix W to only take into account the effect of the guidance knowledge and do not take into the effect of other phenotypes. And then this one is the pairwise constraints. So what we hope to do is that we hope to penalize the cases where the phenotypes have overlapping dimensions. For example, on the first figure to the left, you can see that these two phenotypes, they are highly correlated, highly overlapped, because they have the same hypertension diagnosis and the diabetes. But the ideal one should be that these two phenotypes should be not overlap, just like the figure in the middle. So what we would like to do is that we would like to use a similarity matrix Q, and we would arrive at this formulation. An intuitive reason for this similarity matrix Q is that we would like to have this phenotype 1 and the inner product between this phenotype 1 and phenotype 2 to be as close to 0 as possible. So in this similarity matrix Q, it will only have the ones in the diagnosis and zeros everywhere. So now here comes to the formulation of our objective function. So as we said, this psi contains three terms. The first term is a factorization error. Second one is a guidance. Third one is a non-overlapping constraints. And what we will do is that we will introduce two auxiliary variables, which is called B and U. And we will apply this ADMM scheme and arrive at these Lagrange functions. And you note here, this P and Y, they are the Lagrange multipliers. And next, what we will do is that we will use this block coordinate scheme to solve for these Lagrange functions. And to solve for this is that we will just update each of these variables in a sequential order and until the convergence happens. So here is the block coordinate scheme. First, we will update this interaction tensor, and then we will update this bias tensor. And after that, we will update this Lagrange multipliers. And finally, we will do the tensor completion work and update this full tensor. And we will repeat these procedures until the convergence happens. So basically, this is all about the formulations and the algorithms. And next, we will talk about these experiments.
So we'll talk about how to construct tensors out of the data that we have. So basically, a lot of data we use are time series data, such as what you see over here. And in this particular example, we have information for, this is representing one particular patient, and they have diagnoses and associated medications happening at the same date. What we want to do is capture these co-occurrences of events. So we go through our data with a sliding window, and within any 7-day chunk, when a patient has a diagnosis and medication at the same time, we auto-increment the associated entry in the tensor. This gives it, and then we basically that gives us a count tensor, and we convert it to a binary tensor for the rest of the experiments we do. So we tried this on a couple data sets. First one is a private data set from Vanderbilt University's Medical Center. So both of these data sets, we used 3 modes for the tensor, one for patients, one for diagnosis, one for medications. And then the one from Vanderbilt has about 7,000 patients, 1,000 diagnoses, and 500 medications. And then we used a publicly available data set from the Center for Medicare and Medicaid Services. This one has a lot more data, about 500,000 patients, 11,000 diagnoses, and 260,000 medications. The reason we used these two data sets is we wanted to show that the scalability for our algorithm.
Okay, so the purpose of our experiments is fourfold. So first is about the phenotype discovery. So what we hope is that we hope to show that Rubik actually is able to discover meaningful phenotypes, and Rubik is able to discover fine-grained sub-phenotypes, and it is also can discover distinct phenotypes. And also, Rubik is also robust to noisy and missing data. It is also scalable. And finally, we will answer the question whether all constraints are important. And actually, all constraints in our method are important.
So we'll talk about now how we measured the meaningfulness of the phenotypes that we derived from Rubik. So basically what we do is we constructed 30 phenotypes using both Rubik and a baseline method called Marble. And we handed a list of these phenotypes to some medical experts. So we handed them to several physicians, 3 physicians, and asked them to annotate each one of them and say whether they're, yes, this phenotype is clinically meaningful or possibly meaningful or not meaningful. And as you can see, we found that the phenotypes derived from Rubik, more of them were identified as either clinically meaningful or at least possibly clinically meaningful. So that was particularly promising. Now, this is what the result we got from the bias tensor, which is supposed to capture baseline characteristics of all the patients. What we found was our result for the bias tensor was fairly accurate in terms of modeling what's evident in the original population. Basically, there's a lot of chronic diseases in here, and in the normal population in Americans, 80% of older adults have at least one chronic condition, and 50% would have 2 or more of these chronic conditions. Now we also wanted to show an example of what we call meaningful subphenotypes. So on the left side is a phenotype that we got from a baseline method called Marble. So this one happens to have one element called hypertension. What Rubik can do is separate phenotypes into that include hypertension into 2 subgroups. So the first one includes hypertension as a diagnosis, but also several other diseases, chronic kidney disease, heart disease, and some others. And this whole collection of diagnoses and medications represents metabolic syndrome. And the second phenotype you see here also has hypertension, but has other associated diagnoses and medications. And this represents a patient that has secondary hypertension. So this is how we set up the experiment to identify meaningful subphenotypes. We used 4 guidance criteria: hypertension, type 1 diabetes, type 2 diabetes, and heart disease. And we set 2 subphenotypes for each of these criteria. So 2 types of hypertension, 2 types of diabetes, and so on. So that gives us 8 subphenotypes total. And with the results we got, we gave them to clinical experts for evaluation. And about 2/3 of them were identified as clinically meaningful.
Now I will show that Rubik is also able to discover much more distinct phenotypes. And as you can see, that this lambda q in this figure is the weight of the pairwise constraints, which is also the weight of these non-overlapping constraints. And we can see that as we increase the weight of this lambda q, the average overlap between these phenotypes will of course decrease, and which shows that these pairwise constraints can lead to much more distinct phenotypes. And actually, we can show that this average overlap also tends to stabilize when this lambda q is larger than 10. So we will just set this lambda q to be 10 in our experiment. And the next, we will show that Rubik is also robust to this missing data. To optimize this, what we will do is that we will generate missing data by randomly set the observed values in the observed tensor to be 0. And we will compute a value which is called the average similarity, which is the similarity between the tensors learned without any missing data and the tensor learned with the missing data. And as we can see that compared with all other methods, Rubik is also very robust up to this when the missing data level is still at 0.3. And similarly, we also analyze this noisy data. So similarly, what we can do is that we randomly set the unobserved entries in the observed tensor to be 1. And we also compute this average similarity as our measuring criteria. And we can see that Rubik is also much more robust to this noisy data than the other 2 baselines. And finally, we can show that sometimes we have the incorrect guidance because the medical experts can also make mistakes. So to mimic this incorrect guidance setting, what we do is that we randomly set the entries in the guidance matrix to be 1. And we will also compute the measure of cosine similarity And as we increase its guidance level, we can see that this cosine similarity doesn't drop that much, so which shows that it is also robust to this incorrect guidance. And finally, we test the scalability of Rubik. So what we do is that we increase the number of patients and plot the running time versus the number of patients. And as we can see that Rubik is this blue line. It always takes the least amount of time, and it is around 6 times faster than its competitors. So note that these competitors include both the tensor completion work and tensor factorization work. And finally, we analyze the different components of our constraints. The first one is pairwise constraints, the guidance constraints, and the completion constraints. So what we do is that we will first run Rubik without any of these constraints, which is called this basic one, and it will give you a score. And as we increase this, as we add these constraints to our model, this proportion will just increase. And finally, we can see the contributions of different constraints. So basically, we can see that actually all constraints are important, and this pairwise constraints provide the largest boost. And so for our conclusions is that actually the phenotypes discovered by Rubik, they are all concise, distinct, and interpretable, which is very important for the medical expert. And in our experiments, we show that Rubik can incorporate the guidance from the diagnosis mode, but actually it can also incorporate the guidance from medications and patients, which makes it much more flexible and much more meaningful. And the third is Rubik is also able to be robust to noisy and missing data. It is also scalable. So this is an overview picture of Rubik. Thanks.
Please thank the speaker. So maybe you have time for one quick question. One quick question. Anyone? Okay, let's thank the speaker again and next talk.